So I'm going to continue with the lectures that the previous two speakers have said about sensing. And I am going to talk a little bit about some of the future trends. So where's the state of the art now, and where are the, in my opinion, what's some of the directions where we're going. And then Alex, I think you're, oh, where did she go? Oh, you're going to talk more about like mobile and like the digital sort of sensing.
I'm going to specifically talk about mobile phones.
Yeah. Okay, sounds good. All right. Okay, so we'll get started. And I worked here at the Media Lab both as a student and as a researcher for many years. I was also here as a Europe student when I was an undergrad. And but now I work in mechanical engineering, and I have my own little group called the Mobile Technology Lab. And I also work part-time at MIT Lincoln Lab that does a lot of government work with sensing, which I'll show you. Oh, I thought I heard something. And I do a lot of work in health. So I've been working in the health space for many years. And I currently have an affiliation with Mass General Hospital. So just very quickly, looking at some of the state-of-the-art, what we consider sort of state-of-the-art sensing today. A lot of it is done through airborne and satellite sensing. So MIT Lincoln Labs is one of the world leaders in this space, and they provide a lot of the technologies that are used for all kinds of things like weather forecasting and other sorts of like high altitude sensing. So these are just some examples, and some of this is laser radar hyperspectral, where you look at things from different colors of light, and multispectral imaging. And then here's an example of some of the team at Lincoln Lab installing some of this equipment on an airplane. So one flavor of this is just simply radar, and as you know, radar can go through clouds, so you can image things on the ground or on the sea, and you can do it at night, of course. Infrared is sometimes nice, so you can see things at night, and you don't need light illumination. Here's a picture of MIT with the infrared. You can see the Great Dome, and the Media Lab is right there on the edge, on the right edge of that image. And there's a variety of really nice technologies, which I won't go into, which you can do from an airplane now with laser radar scanning. And here's an example of the laser radar scanning of Boston. So that's an image of Boston. So you can get a very high resolution 3D map of a city or a region. Just to give you sort of, what are some of the state of the art that you can do today. So here is a Halloween mask. Tomorrow's Halloween. So there's a Halloween mask. And this is a laser radar example. So that image right there is taken from a state-of-the-art laser radar imaging system. And you can see that you can actually, this is from like 20,000 feet up in the air. You can get a pretty nice view of the mask. So you could almost see like all the pimples on your face, from an airplane, with this kind of technology. So these are some of, kind of a chart of some of the pros and cons of each one of these, kind of like how wide the sensing area is, day or night, is it 3D or not. But you see the real power is in putting a lot of these data sets together. So I wanted to mention something that was sort of in the news this week, and just yesterday I heard this story on NPR that an example of laser radar system was used to discover a previously uncovered or undiscovered Mayan temple. This is in the Yucatan Peninsula, kind of the southern tip of Mexico near Guatemala. And you can see here an example where it's usually covered by the jungle, but with a laser radar technology, you can essentially strip away the vegetation and you can see the topology underneath, and you could see all the structures, and here's like a Mayan temple in a laser radar data format. And another very big consumer of this type of technology is the agriculture industry, right? So in the US, of course, we don't have like subsistence farming. Farming is done by very like mega corporations. So these large companies do, and the government does a lot of imaging for agriculture purposes. And this happens at multiple scales. And one of the interesting things, as you might know, plants are living things, right? So living things, in particularly plants, have chlorophyll, and chlorophyll has a property called fluorescence. So basically, you excite it at certain lights, and it emits light at other wavelengths. And using some of those spectral properties, you can actually get a lot of information about the crops, like where there's a drought, or if there's an insect infestation, or some other properties of the farm or the agriculture field. So this is done at the ground scale, sort of. They have towers on the farm, they have drones, they have airplanes, and finally it's done with satellites when you need a really large area. But of course, satellites don't have the resolution that you can get with, like, let's say, an airplane or a drone. And there have been companies, in fact, there was an MIT startup company that won the 100K competition several years back doing drone sensing for farms. They've now shifted their business model, but that was an interesting example. And of course, the world is moving towards satellites. There are thousands and thousands of satellites all over space orbiting the Earth, and they're in all different types of satellites, so you can essentially do sensing all over the world. Now, of course, getting access to the data depends. There are many private companies, there are governments, but the satellites are there. And there are many data sources which are, some of them are free, some of them you have to pay for, but there's a lot of data sources and services which you can actually get access to and do data analysis. So this isn't all like, secret government work. Like, there's a lot of open data sources for satellites, a lot of commercial companies and commercial data that's available. So now I'm gonna, that's sort of the landscape of state-of-the-art sensing that's used commercially and government-wise. But now I'm gonna just talk about some of the trends that I see in sensing as it overlaps with some of the work we've done here at MIT. And what does it look like in the near future? So I think one trend is, I think things are getting a little bit more local and personalized. So I work a lot on human health, so I'm interested in the sort of sensing as it intersects human health. And as Andres may have mentioned, he talked about different layers of sensing and different layers of data. And I have here it mapped out in one way of mapping it out. Of course, there's genetic information. These are all the things that affect your health or impact your health, right? So there's nutrition, there's a social aspect, and your health is, you can monitor physiology, your vital signs directly, you can monitor your psychological parameters, and then there's the big, environmental. And I also want to mention, which I'm not going to talk about, is we all have a very big footprint and signature in the virtual worlds, in the digital space. So there's a whole universe of sensing techniques and research being done in the virtual world to look at your digital footprint, known as digital phenotyping. And that's some of the work that we're currently doing with phones, et cetera. And one of the origins of this was actually here at the Media Lab. So Professor Sandy Pentland, one of his students, Nadav, started this project called FUMF.org. I think the website is still up, at least it was a couple months ago. This was one of the very first examples of mining the data on your cell phone to monitor and predict behavior. So I'm going to mostly focus on environmental sensing here. And when I was a student, one of the more well-known projects, I guess, that I did was sensing the weather at the top of Mount Everest. So we collaborated for 2 years with teams that were climbing Mount Everest, and then the third year we did Antarctica. But basically, we had to build a little miniature weather station that got sent up to Mount Everest, and the data was collected via satellite. So it was a low Earth orbiting satellite. Our little weather probe would transmit the data up, and then it would get picked up by a satellite, and then get dumped over France, and then we'd receive it back over email. Then over the years, things got a little bit more portable. Some of the projects I did for India, we did handheld monitors, which are mobile. You can actually take this. So I worked with the pollution monitoring boards of certain cities in India, like Chennai, and they can go out to a dump, do an assessment, and see what toxic gases are being released, at certain, like when there's an environmental event, like a spill or something. And then there are local companies now. So some of my friends that we worked together when we were students, they now have a startup called QuantAQ right here in Somerville, Greentown Labs, and their startup is called QuantAQ. If you want to know more about that, you can look at their website, and they'd be happy to host you if you want to go visit. They make a really nice air quality and environmental monitor. So we know air quality is important for health, not only for pulmonary, but it also affects our brain and our heart health. Then there's also indoor pollution. So a lot of the world's population cooks on a biomass stove, right? So they don't have the luxury of electricity or gas. So that causes a lot of air pollution and health problems. And then there are other things in the environment which we don't often think about, things like sound. So different types of sound are coupled not only with sleep disturbance, but even things like cardiac, strokes, blood pressure, and a lot of mental health conditions. Light is very important to health. And by the way, each one of these slides is like a half-hour lecture, so I'm going really fast and just skimming across the top of these topics. But light is a very important part of our circadian biology, right? So our eyes are connected to our brains, to our neuroendocrine system. And for example, you probably all know that when you shine blue light, it suppresses our production of melatonin, so it keeps you awake. It's like drinking, a cup of coffee. So light is important. You don't want to have blue light at night. And then another very important topic is heterogeneity, right? Humans are very different from each other, and that's something that's often an issue in research because a lot of the papers in academia, we might do a study with, say, that like 30 people or 50 people, but those people are all students, and they're all like 25 years old. They're all relatively healthy. So the data that we get is not really representative of the real world, right? And the same thing is true when companies develop a drug and they test it somewhere. They're often testing it on a particular population so that those results and those models have bias. So you have to ask, what is really average? What does average mean? And we know that a lot of the health effects are driven, and our vulnerabilities are driven by genetic variation. But we also have this thing called epigenetics, right? So the expression of our genes depends on our environment, and also things like chemical exposure, even our emotional. So the way that we develop and the way that our genes are expressed. So you may have two identical twins, but they may develop differently if they grow up in a different environment. So that's epigenetics. And one example, this is just kind of a simulation which you could look up in this paper. So if the air quality, let's say we had a small amount of air pollution in a community, how much is that going to raise the risk of having a heart attack? So you might think that, okay, the risk might go up slightly. So here it went up, 5%, right? A small increase in heart attacks. So, but in reality, that's not really true because that assumes that the population is, number one, healthy, and number two, that they're all identical. In reality, it looks something like this. You have a small fraction that get an elevated risk, and then you have a much smaller fraction that have a significant, so that small change in air pollution actually impacted them a lot, and they have like a 25% higher risk of heart attack. So that's the sort of thing that you find in the real world. Now here's an example from Washington, D.C., looking at, air pollution, but overlapped against the incidence of diabetes. And you can see people who have diabetes are more sensitive to changes in air pollution. And there's now a whole field, there's whole conferences on something called environmental justice. Right? So there are professors at MIT who have, working with that startup that I just mentioned you, SenseiQ, and they're doing, they have a whole network of air pollution monitors in different neighborhoods in Boston looking at sort of like socioeconomic factors overlapped against like environmental conditions. And there's also, they also work with Native American Indians. So Native Americans is one of the marginalized groups that also struggles a lot with air pollution. And the problem here is not technology, but education, right? Literacy. How do you train people in these communities on these Native American reservations how to interpret and understand and air quality data and how to make use of it? So the implications is that there's a lot of other factors, and humans are not all the same. How do we make this more local and personal? So we have these large monitors, for example, that are run by the state of Massachusetts in this case. If you looked at the past 20 years, you've seen people make and publish sort of portable monitors. So they started out being things like the size of a backpack, and then there's little 3D printed Arduino-based sensors with a mobile app. But the problem with a lot of these is that the sensors used are a little bit too cheap, and it's really difficult to calibrate and difficult to compare your data against the data with like your neighbor's data. So it really depends on the application, but for certain applications, you want to have some level of calibration and some confidence in your data, and you want it to be reproducible. So we use electrochemical cells made in the UK and England, an MIT startup there called AlphaSense. And they make like the world's most sensitive electrochemical cells. So I made this little portable board that you can actually wear on your body, and it measures a variety of things, including sound and light and humidity, temperature, even accelerometer, so it could detect when you're walking, in addition to GPS. So you can wear this like you see in this picture, and you can also, it's small and light enough that you could even put it on children. So the idea is that you are measuring your own personal exposure to air pollution. So you're not just measuring the source, but since people move around, you're measuring your personal exposure to air pollution as you go about your day. So we did the usual thing. We built a mobile app. We built a website. The website's not up anymore, but that's sort of what we did. Okay, so the second topic, and there's only two in this talk. So the second topic I wanted to say is, with regards to putting sensing inside buildings. So another trend that I see is, aside from wearables, we want to make sort of, you've probably heard the term ubiquitous computing, right? The Mark Weisner sort of vision from the 90s. So we want to have invisible computing. We want the computing to be embedded in our space where we live, but the same thing with sensing. We want the sensing to be embedded in our space, so we don't even see it. So I don't have to wear a wearable. The sensing is just part of the building. So, over the years, I've worked with building wearables and sensor systems for human, autism. I've done sensors for monkeys with Course 9, with the monkey labs here. We've done sensing for plants. Chlorophyll fluorescence is an example of some plant data that we did. And City Science was also home for a big project at the Media Lab called City Farm, where we started out with one room like this, where we were actually growing food at the Media Lab, and it grew to be this size for a few years. That's me right here. And so we essentially had this controlled environment where we could control exactly, like you can dial in the parameters that you want to grow a specific thing, whether it's like tomatoes or a particular type of cotton or something. We had different sponsors at the time. And the group made these little boxes where you can give this to a school, and you can have a school that as an education project has this little controlled environment for growing a plant, right? What if you could have a controlled environment for humans? So what if we had full control over our environment? How can that be useful? And how would that affect our health? So with regards, in the context of architecture and design, Churchill had this famous quote, which is, "We shape our buildings, and thereafter our buildings shape us." So the idea is that the architecture that we design affects and influences the social structure of the people that are going to use the building. A very good example is the Media Lab buildings itself. The original Media Lab building was built as a studio space, very small, intimate spaces, a lot of walls. It was used kind of for art studios, music studios. Then as the needs changed, we designed this new building, and this new building is completely the opposite. Mostly glass, you can see everywhere, there's no privacy, and it completely changed the way that people interact. Like, of course, so you might imagine, where do people socialize? They come here to the open building with glass to socialize. If you want to be by yourself and get some work done, you go to the old building that has private spaces. So the shape of the buildings that we design affect us. And there's in fact a whole field of architecture and psychology called environmental psychology, where things for people who make, for example, who design hospital rooms. So they're like, okay, you want some plants. If you want people to feel better, they're healing. You want a more positive, healthy environment. You want plants. You want green things. You want fresh air. You want good sound, color. So all these things in your environment have an impact. And it is possible to design a little pod that has all of this built in. And there is a hotel which I've stayed on, and there's a few of them around the country, but it's called the Even Hotel. And they have a fully controllable environment. There's no AI here, but you can actually dial in the environment. And there's a Media Lab legacy for this. So it's not just my idea. This is all like Media Lab. So Nicholas, of course, started he was co-founded the Media Lab, but he started the Architecture Machine Group in '67, which is a long time ago. And the idea was embedding, just the dream that I said, embedding sensors into the architecture itself. And we had this project in the '70s, former Media Lab faculty, Dick Bold and Chris Schmant. These are very famous. You can still find this on YouTube. And the idea is, how can you build a smart space that can sense our gestures and also display information? Then my advisor, Neil Gershenfeld, then continued some of that work in the '90s, saying that information is not just this virtual, but it has a physical impact. It has a physical properties. And then designer Hiroshi Ishii, who is just around the corner from this room, he based his whole career at the Media Lab on tangible bits. How do you bring the interface out of the display, out of the graphical display of the computer, and embed it into the space so you can feel it and get not only touch it, but have it touch you and affect you. So I see this as sort of this feedback loop where you have sensing, but you have this actuation. So you have AI that can run all these algorithms and models, and depending on what's happening, depending on your health state or your physical state, or depending on what you need, the environment will respond to you in real time. These are all the different things that you could measure non-contact without a wearable. Obviously, you could measure your light, sound, even your smell. We've built smart mirrors. There's applications for security. So we've done radars. With a camera, you can non-contact measure your heart rate and respiration. These are all old Media Lab projects that we worked on. You can embed this into a phone, so we have a tablet that could measure your heart rate while you're using it. And we have thermal imaging. So from thermal imaging, there's now little modules that you can plug into your phone, and you can non-contact measure your respiration, and you could non-contact screen for disease. So we can detect pulmonary disease and things like what's your chance of having COVID. I won't go into the health reasons for this or the physiological reasons, but depending on this is measuring the thermal patterns of your face. It's not measuring just temperature, it's measuring the patterns of the temperature in your face. So from that, there are certain diseases that you can actually detect with this technology, even things like diabetes or COPD, things which may not be obvious that you can detect from a thermal camera. And we use AI techniques such as saliency maps, so you can actually see what is the AI model looking at, and why does it think you have diabetes? Like, what part of the face is it looking at? And in my opinion, I think the future is smell. So everything has a smell and chemicals. So smell, there's a lot of artificial nose technology that is doing chemical sensing at a distance. So dogs can do this already, and dogs can detect things like cancer. Even a dog, so the term the smell of fear is actually real. You can actually detect when someone is afraid just by the smell of that person. Like your sweat glands open and you emit certain smells. One of my friends, Andreas Merschen, who just recently left MIT, but he was here for decades, and now he's doing a startup with artificial nose. So once you have all this information, you can actually do interventions. So you can actually apply light, apply heat, apply smells to impact your health. So you can change the color of the light, you can change the sounds, you can add different smells, and this is all starting to be used, for example, on airplanes. There are companies putting like lavender smell to relax you, and Judith Morris is one student who worked on this, if you want to look up her PhD thesis. And there's a lot of work being done on neurostimulation. So again, this is sort of a summary of the model. And we did a patent on this a couple decades ago. And I like to change the Winston Churchill quote to this, that we shape our technology, but our technology shapes us. And I think that's very true. The technology is really changing human evolution. So there's many applications. One of the big ones driving this, of course, is the aging population. We have a huge percentage of the population that's aging, and we don't have enough young people to take care of us. So we're going to need these technologies. So it's out of necessity, I think this is all, even though this doesn't get much attention, this should, because this is really like the number one need that we're facing in the medical field over the next like 20 or 30 years. So in conclusion, I guess to summarize all this, the past 30 years, I think there's been an explosion of sensing. There's been all kinds of sensing from ground to satellite. But I think the future technologies where there's the field is currently growing is more localized and personalized information and sensing, number one. And number two, adding AI so that the space around you can respond to that sensing information and provide real-time feedback or interventions as needed. And that's basically a user interface or interaction design problem, which I think is a good match for you, what you guys enjoy doing. So I think I'll end there, and there's my contact info. Thanks.